So last time we have been discussing about the reverse orbit determination problem. We are given AEI, etc., and then we have to determine x, y, z, x dot, y dot, z dot. We are following the previous discussion. Dissolving R along ON and OM direction. So this will have components along the ON direction and along the OM direction. So this is clear here that R cos theta plus omega minus 90 degree, this will be along the OM direction. So from here we can write R sin theta plus omega. And along the OM direction we will have R cos theta plus omega. And this is the initial x, y, and z direction. Now OM component, okay, let us first work out the ON component. So ON component can be broken along two directions. One along the OX direction, another along the OY direction. This is along the OX direction, and then along the OY direction, this will be R cos theta plus omega and sin theta omega. Let us name this as, or either leave it without naming. Then next we have the OM part. So this part is broken along the two directions. OM part we have to break. Now the OM part, this can be broken along two directions, one along the OZ and another along the OM prime. The OZ component will be R sin theta plus omega sin cos psi. This angle between this line in this axis and this is 90 minus I. So cos 90 minus I means sin I. So along the z direction we will have only this part, but along the x and y direction the other contributions are there. So still OM prime is not along the OX and OY direction, so we need to break it. So as we can see, OM prime, this will have component along the OX direction as R sin theta plus omega cos I times cos 90 plus capital omega. Cos 90 plus capital omega. This is minus sin capital omega. So we put a minus sign here. And then along the OY direction, this will be simply cos capital omega. The angle between this and this is capital omega. This angle is capital omega, so this is 90 minus capital omega. This angle is from here to here, this angle is 90, so therefore we get this angle as capital omega. So all this we have these components and we need to add them up and work out. Having components along the x, y, orbit direction. Along the OS direction we have coordinates of the point R will be given as R cos from the previous page I am writing it R cos theta plus omega and then minus R sin theta plus omega and 5 times sin capital omega. So these are the coordinates of this satellite in the initial reference frame. The next step is easy, but little lengthy. That in order to get the H dot, we just need to differentiate the corresponding equation. So we will get here R dot and R times, then we have to differentiate the quantity inside. So we will have here cos capital omega, small omega, all these things are constant. So whichever the quantities are constant, we need not differentiate, only theta will get differentiated. Therefore we get here in this place minus sin theta plus omega and cos capital omega minus r cos theta plus omega psi times capital omega times theta dot. Here r as usual we get it from this equation e times cos theta theta dot is equal by r square. So L by 1 plus e cos theta, this is nothing but r. So we remove that, then e sin theta is divided by r times 1 plus e cos theta is L. So therefore r dot is known to us. Because theta is known, L is known, E is known, H is known, and therefore r dot is known. And r is here known, theta dot is known, so just insert in this equation and the result will be available. So we can summarize H dot as H sin theta divided by L times theta plus omega r we can keep it as it is instead of breaking it. So here theta dot is there, so this quantity is h by r square. So here we can write it h by r sin theta plus omega capital omega this is the expression. The same way expression for y and z can be obtained, y dot and z dot.
Sir, in the second term, you took r common outside it.
This one.
Yes, sir. Just the before step of that one.
Oh, r is that r will not be present. R is already in common. And here also r is not present in this case. It's a pretty simple, straightforward. Only thing that we need to maintain track of the various quantities. So I will skip y dot and z dot. Is it okay?
Okay, sir.
Or let me summarize that part here. spectral omega outside. And then we will have spectral omega. Where L equal to A times 1 minus E square, H equal to S square equal to mu times L. Mu is known, L is known, and therefore this quantity can be computed. So one thing you should notice here that we have kept all the parameters as constant and only theta is varying, the true anomaly. In the orbit, well, we are referring to the focus, so this is your theta and this is the only quantity varying. Rest other things are remaining constant. Orbit does not change, A remains constant. Eccentricity does not change because the perigee position remains the same, therefore E is also a constant, and other quantities like the small omega, capital omega. So until unless there is perturbation, all these quantities will remain constant. And such kind of orbit is called the Keplerian orbit. Keplerian orbit. If suppose instead of the satellite following this ecliptic trend because of perturbations from planets and gravitational forces, it follows some route, some other route, which is neither hyperbolic nor you say it can happen in this way that your orbit is not closed. So because of the perturbation, it's going down like this. Orbit may be rotating. The A may swing. Okay, this kind of figure can appear. So in that case, at any instant of time, wherever the satellite is there, either in this position or this position, so at this point, say here in this case, I am showing this orbit and therefore will not take this point, or either you show on any other point, let us say this point, and then the orbit I shall show it like this. Satellite has come along this line. Okay. Now if it is Keplerian orbit, it will follow this path, but if it is not a Keplerian orbit, it will go along some other direction, and this happens because of perturbation from Earth itself, because the Earth is bulged on the equator. So the gravity consists of infinite number of terms, okay, which we have to model properly using the Legend's polynomial. So the satellite will follow some other path, but at any instant of time, given the x, y, z and x dot, y dot, z dot positions of the satellite, immediately you can think of one orbit like this, where the center of force here in this case it's located here, so it may look like this or any other shape. Okay, so this orbit we call as the oscillating orbit. This is the true trajectory. what the satellite will be following. And this is just touching at that point. So osculating means it's just touching at that point. So osculating orbit. So osculating orbit is drawn just like Kepplerian orbit, only thing that it's only valid at a particular instant of time. This is valid for all the time. No perturbation, all the time it will remain like this. While here in this case, the osculating orbit, sometimes it is here, another time you will see here just like it's a changing. Okay, so you can think of one orbit at any instant of time. Once it goes here, so if this is the center of force, so then you can consider this orbit to be touching this here and going like this. So another orbit. Okay, so the oscillating means it's just touching at that point. And it's drawn like the Keplerian orbit, but it's not a Keplerian orbit. Because the Keplerian orbit, all the parameters remain constant except the theta value. While the oscillating orbit is valid only at a particular instant of time. Thereafter, it does not exist. Thereafter, new oscillating orbit will get generated. Okay, so once we have finished this, then comes the problem of the orbit propagation. So in the orbit determination problem, we can discuss it like this, that given R0, V0, find RV at any arbitrary time t. Its inverse problem has been given AE I small omega capital omega theta, find RV at t. So just we need to convert these elements to x, y, z as a dot vector and z dot, where this theta belongs to theta equal to theta t. And what we have already done, which is given R0, V0, find AEI small omega capital omega theta. So this problem already we have done. This problem already we have done. This is the problem that's shown here, which is called orbit propagation. Of course, you can integrate numerically and work it out. So R0, V0 at T0 is given, then find RV at T. And there are two ways of doing this. Solve this equation, minus mu by R2 bar, integrate it numerically, numerical integration. And here we can have another method, what we call as the Kepler's equation. So here what we do, find elements. So given the R0, V0, to find elements, AEI, etc. Capital omega theta So all these five things are quantities are constant. Theta is varied. So theta is a function of time t to propagate theta. So instead of directly propagating theta, it's propagated in terms of what is called the eccentric anomaly, in terms of E. Eccentric anomaly. So propagate in terms of E and then solve the problem. Why this quantity E is being brought out, we will see shortly. E is called the eccentric anomaly. Let us have a look at that, what that quantity is. Say we have a circle here. This circle I have drawn, so on the page shown to you, it's a distorted. Then another circle we have. Draw a line like this. Then draw perpendicular from here and draw horizontal from here. So this way, just keep doing it. And then match all these points. Match these points. And whatever the locus is generated, it's called ellipse. And you will find some interesting properties in this. So once you have drawn the ellipse, so this is the center of the ellipse. Focus is lying somewhere here. This is your focus. Any point, let us say we are taking on this. So this is your R. Draw a perpendicular here like this. And let us say this quantity is P. This is M. Okay. So this quantity from here to here and this quantity, they are in a particular ratio. And this property we are going to utilize to work out the problem here. So I am not able to draw a good figure here because of whatever I draw, everything gets distorted on the screen. And this is a great challenge for me. Unless I draw a vertical ellipse, it will not appear as a circle. So using this method, we can work out all the details, and just keep in mind this figure is very useful for solving your problem. So the same figure is shown here. So we can show it in some other way also. We have an ellipse here, and surrounding this we have the circle, which is called the auxiliary circle. This is your focus. The point P can lie here, and then vertical drawn from this place. This is M and this is N. So we will work out all these things. For the time being, we'll assume that this ratio is known to us, and then do some theory part. In the next class, I will do all those things. So let us start with so the Pn divided by Pm, this quantity we write as d by q. And if you try to do it yourself using that figure I have drawn on the previous page, immediately you will see that okay, it's clear. There's nothing problem in that. Why? Because once we draw a line from this place to this place, which is called the auxiliary circle, this angle is called the eccentric anomaly. This is a true angle. It's a visualization geometric angle. And where it is going, the point P is raised above and it cuts the auxiliary circle here. This part, this height, the figure is really an issue. And if we extend this, it goes and cuts here. You can directly see here. So this quantity is shown in the black. This is your A, the semi-major axis, because this is the radius of the circle. Inner radius of the circle is B. This part is B. So this quantity from here to here, this angle is P. So this quantity is B sin A. B sin. And similarly, the quantity which is present here, this is A sin A. You can check the ratio. This is Pn divided by Mn is nothing but B by A, the ratio of these two quantities. So this becomes apparent only if you work using this figure. So this is the geometric property of the ellipse which we utilize here. So with this given information, Pn by Pm equal to B by A, we do not have any tool for drawing. Okay, whatever we have here, we will work with that. The focus is here, in this point, F is line, this is your R, this angle is theta, the center is lying here in this place, this is the center, this quantity is B, this is A, this is N, M, and this point is P. So the quantity from here to here, this is A times C, and this quantity is A times 1 minus E. And then the angle, this is the eccentric anomaly. And E and theta, they are connected together to certain equations. So immediately we can see from this place that x equal to r cos theta. We have drawn this figure, but this is true for all the situations. Say here this is your focus and this is r. So this is your r equal to x equal to r cos theta and y equal to r sin theta. So you can utilize maybe this figure. This is the focus. Center is lying here in this place. So this distance is A. So then x can also be written as x equal to r cos theta equal to AE with a minus sign. What we do here, we write with a minus sign and then plus. This we are raising, and this is going and cutting this auxiliary circle to which we are drawing this angle P, then this is A. So this is A cos P minus, what is A? A is this total from center to the this position. So A cos C or either this whole thing. Because of the behavior the circle we have made. So that this becomes A cos C. A cos C. And from there then we are subtracting this minus A. So minus A times A cos C. And by simply it becomes D sin A from the previous figure. And if you want to write y equal to r sin theta equal to Pn, and then Pn can be written in terms of from this place d by a times Pn. This we are written from here, this is like Pn by Mn. So this is Mn. So Mn is known to us, which is nothing but A sin E. So therefore this becomes B sin E. So either way, whatever way you want to write, it's okay. This is R sin. So R cos theta is known to us. R sin theta is known. Therefore, R can be described in terms of eccentric anomaly and A. Mathematics is not much complicated. It's a simple. If you remember this geometry, then it's possible that you can work it out anytime. So this becomes this square and then plus d sin e cos square e minus 2e cos e plus d square, and b square becomes c square times 1 minus c square. This quantity can be added. So this is 1 minus 2e cos e plus d square. And then minus e square sin square. Okay, so these two can be combined together and can be written as 1 minus 2e cos e plus cos e square cos square. As r is always a positive quantity and therefore we can choose this as. So if r is described in terms of the semi-major axis, eccentricity, and the eccentric anomaly. And this will be quite useful while working later. Similarly, cos theta, r cos theta is equal to x, and x we have written as a times. On the previous page, we need to go and check in there. This is a times cos e minus. This is what we have written on the previous page, or either here in this place it is given. So therefore, from this place, cos theta becomes and this is how your theta is related to eccentric anomaly. The true anomaly theta and eccentric anomaly, these are all physical quantities. Later on we will see one the mean anomaly quantity which is indicated by capital M, and that's a totally purely a mathematical quantity. Okay. As such, no physical representation exists for mean anomaly. Okay, so what we have worked out cos theta equal to this can be simplified a little bit. This cos theta can be written as 1 minus tan square theta by 2 okay, because the cos theta we write as cos square theta by 2 minus sin square theta by 2, which you can divide by cos square theta by 2 plus sin square theta by 2 without any alteration, and then divide the up and down by cos square theta, numerator denominator, and this will give you this equation. So this quantity turns out to be, okay, so we are going to utilize this expression. So using componendo dividendo from your 12th class, we can write this as 1 plus tan square theta by 2 plus, or say the minus 1 plus tan square theta by 2 divided by plus 1 minus this will tan square theta by 2 1 minus 2 and then this equal 1 minus 2. This expression between theta and E is a little more simplified. And we can see that as theta increases from 0 to pi, then E increases from 0 to pi. Okay, so later on we are going to use all these results for solving this problem. What we have to do, that we need to propagate the orbit. This is our objective. So propagating the orbit, we take this equation r square theta dot equal to h and write this as d theta by dt equal to h by r square, or dt equal to r square divided by h d theta. And integrate it. Where r is a function of r equal to L by 1 plus e cos theta. So integrating it is not as straightforward. For the parabola, you can integrate it just directly, but for hyperbola and the ellipse, we need all this manipulation what it said described here. So there are three ways we can do the problem for the ellipse, hyperbola. So I will take up those approaches in the next class. So we stop here today with the results that we are going to utilize further. If you have any question, you can ask me. So today, yes.
Sir, in the expression of tan theta by 2, it should be root of 1 plus e upon 1 minus e.
Here is trying this part is missing. Anything else?
Also, sir, could you once again explain why we did, like why we converted theta in terms of e? Like why are we not working in terms of theta, but working in terms of capital E.
Okay, and yes, I will show you. Okay, the problem is with that, just I told you that to get the ephemeris or the position in the future, we need to work with this equation. For this we are writing as r square divided by h d theta. So here in this case, this is L by 1 plus E cos theta whole square. And outside we can take it as h, this becomes whole square, and this is d theta. Whole square divided by h d theta by 1 plus E cos theta. So this we need to integrate. This integration is not a straightforward. Either you look into your calculus. We have, of course, once we go to the hyperbola part, at that time we will consider all those things. But number of approaches is possible. So in the calculus, you do certain manipulation by replacing this term with certain thing, and then to try to solve it. The same thing is being done here in this case. This is not directly integrated. On the other hand, if this is the case of a parabola, so this is simply 1 by cos theta whole square, because in that case E equal to 1 for parabola. And this you can integrate directly. For this quantity 1 plus cos theta is nothing but 2 cos square by 2 whole square. Okay, L square by 4 h, and then f to the power 4 theta by 2 and d theta, this integration. This we can get into two parts, h square theta by 2. H square theta by 2, which we can write as 1 plus tan square theta by 2, and then try to integrate this. So directly this integration is available, but not in this case. When e equal to not equal to 1, so we cannot directly integrate. And therefore, to work out this, we need to do all the manipulations, what we have been doing here in this class. So we will utilize this, and we will do by other methods also to solve this problem. What we are solving this problem. To get the future position of the satellite. The future position is because A, E, I, small omega, capital omega, all these are constants. Everything theta is changing. So theta, instead of directly estimating theta, if we can estimate E, then our job will be done. So later on you will see that m equal to n times t minus capital tau, small tau. This quantity is equal to E minus E sin A, where m is the mean anomaly. N is the mean angular velocity. As in the case of ellipse, we have looked. So at any time t, we can solve for this E, and then we can solve for theta.
Sir, so basically all this we have done just to simplify the maths, right?
Just to simplify the maths and find out the future value of theta.
Okay,
Because
sir.
it's difficult to work with this. Numerical integration anytime you can do, there's no problem. But analytical, there is problem. So this is done indirectly. The next class is the thing to do on this.
Okay, sir.
Please respond to your attendance.
Sir, I had a question.
Yes.
So basically, when you talked about oscillating orbits, can it happen in 2D, like only, say, capital omega is constant, but other parameters change, or capital I is constant and other things change?
No, the inclination does not change. Not capital I, we show it by small I. So this inclination, this is capital omega. It can happen that, but that kind of orbit, it's a, you will see that once it's changing, so the various parameters will change. In the case of, if you are looking only in plane change, that happens in the case of the aerodynamic drag. For the aerodynamic drag on the satellite while it's moving into orbit, so the aerodynamic drag, that it's a solar panel is having, this is having the central body. So, and the molecules are striking this. So because of that, the aerodynamic drag is produced. This can be written as 1 by 2 rho V square S times CD. This is the cross-section area, just like in your aerodynamics course, the flight mechanics you do. So this drag, it will reduce the energy, the E prime equal to mu by 2a with minus sign. So this starts decaying. So that means it becomes more and more negative. Okay, and that can happen only if A becomes smaller and smaller. So A decays. That means your orbit here, once you are looking in this particular figure, I'll go to the next page. In this figure, so this is the focus here, and satellite is here. So continuously, then this will shrink. That means the orbit will look like this. It's a continuously shrinking. This is the only in-plane change, without change of inclination and other parameters.
And argument of perigee cannot change in plane.
Argument of perigee can rotate.
While staying in the same plane.
See here, if v is the velocity here, and if you produce any change delta v here, the argument of perigee remains the same. But if anywhere any extra impulse it receives, the argument of perigee will change. So this will come to once we do the trajectory transfer. So at that time, those things, many problems we will have. Okay, so for changing the argument of perigee, it's necessary that except at the perigee position, you give impulse somewhere else, and then the argument of perigee will change. Otherwise not. Here in this case, it's the only A is decaying.
Okay.
And then once we do the Gauss equation, so at that time we will have further look into this. This is called the Gauss variational equation. So in that, the perturbation of the orbit, how it's changing. So almost once we look through the gravity, so almost all the terms will be getting affected because of the gravity. The capital omega by dt, the small omega by dt. So you will get the Gauss variational equation. Or either the okay, we'll come to this part later on, because this is not of anything I tell at this stage, it will not be clear to you. The energy decay that results in the change in the field. For changing the argument of perigee, you need to give impulse, and while this is changing, so your orbit becomes a oscillating orbit. It's a continuously changing. It's no longer a Keplerian orbit. The plane will not change. That means the capital omega and I, they are not changing. Your A is changing, E is changing. An argument of perigee, for that change you require impulse at certain other point so that it changes further. Otherwise the symmetry will be maintained. Okay, any other question? So please respond to the attendance. Shivam, Raghav,
Present, sir.
Vivek,
Present, sir.
Parth,
Present, sir.
Hariharan,
Present, sir.
Giri, Shaurya,
Present, sir.
Ashish,